I was looking at the stack of sources we pulled for today, and I honestly didn't know where to file it in my brain.
That's a weird one.
It really is. Usually we're looking at, say, a new battery tech or a geopolitical shift, things you can touch, things that feel real. But today's different.
I agree.
We're looking at sources that are trying to bridge this gap between what sounds like total science fiction.
Like movie stuff.
Exactly. Stuff from The Matrix or Blade Runner. And what's, well, rapidly becoming science fact.
It's a fascinating collection. I think the best way to frame it really is that we're looking at the source code of reality itself.
The source code. I like that.
We have papers here that range from the subatomic level, asking if information itself is, a physical thing, all the way up to fusion reactors.
Massive scale.
And the common thread, the thing tying it all together, is how we're using data, how we're processing information to sort of master nature.
Hacking it almost.
We are seeing a real shift from just observing the world to actually, hacking it.
Well, hacking nature is a pretty bold claim, but looking at this first topic, it might not be an exaggeration. We are starting with the biggest question of them all.
The big one.
The one that always comes up in those, late night dorm room debates.
Up to one too many coffees.
Exactly. Do we live in a simulation? And normally that's just a fun thought experiment. But we have a source here about a physicist, Melvin Vopson, who's basically saying, I'm done guessing. I want to prove it.
And not with philosophy, with physics.
That's the part that gets me.
That is the key difference, right? To really get what Vopson's proposing, we have to go back to where the theory started, with the philosopher Nick Bostrom back in 2003.
I remember reading about that, but Bostrom's whole argument was just probability, wasn't it?
Precisely. A statistical argument. Bostrom said that if an advanced civilization ever gets to a point where they have, near infinite computing power.
Post-human civilizations, I think he called them.
That's the term. He argued they would almost certainly run simulations of their ancestors.
Ancestor simulations.
Yeah.
So just to see how history played out.
And they wouldn't just run one, they'd run billions of them, tweak the variables, see what happens if, the dinosaurs didn't go extinct.
Okay, so if you have one base reality, the original universe, and then a billion simulated ones, well, the math doesn't look great for us being in the real one.
The odds are 1 billion to 1 that you're in a simulation. It's compelling logic, but it's just math. You can't touch it.
It's not physical proof.
And that's not good enough for Vopson. He's a physicist. He wants to find the code. He wants to find the pixelation in the universe.
And this is where my brain started to melt a little bit, because he's proposing a new law of physics to do it. He's talking about information as a physical thing.
This is the absolute core of his theory, and it is a heavy concept. He calls it the mass-energy-information equivalence.
Okay, break that down for me. We all know Einstein, E equals mc squared. Energy and mass are interchangeable.
Right. It's the equation that defined the 20th century. Vopson is trying to update it. He's adding a third piece to the puzzle.
Information.
Information. He's arguing it's not abstract. It is the fifth form of matter, right up there with solid, liquid, gas, and plasma.
Hold on. Explain this simply. If I have an empty hard drive, and then I fill it with a terabyte of movies, does the hard drive actually get heavier?
According to Vopson's theory.
Yes.
That feels impossible.
It sounds it, but it's based on something called Landauer's principle. Back in the 60s, a physicist at IBM, Rolf Landauer, realized that information isn't free.
What do you mean isn't free?
He found that when you erase a bit of data, when you flip a 1 to a 0, you have to release a tiny, tiny amount of heat. You increase the entropy.
And heat is energy. Exactly. And since E equals mc squared, if erasing information releases energy, then storing it must mean it has mass.
So the 1s and 0s on my drive physically weigh something because of the energy state they're in.
You've got it. It's an unbelievably small amount of mass for 1 bit, but if you scale that up to the entire universe, every single particle has data about itself. Its spin, its charge, its position. It adds up.
So the universe isn't just containing matter. The universe is a giant hard drive.
And like any hard drive, it has to manage its data. Which leads us to the glitch he found, something he calls the second law of infodynamics.
Infodynamics. That sounds intense.
It's a deliberate play on the second law of thermodynamics, one of the bedrock rules of physics.
That's entropy, right? Chaos.
Yeah.
Everything tends towards disorder.
Correct. The universe naturally moves toward chaos. Things fall apart. A hot coffee gets cold. But Vopson looked at information systems, digital storage, even the RNA of the COVID virus, and he found the complete opposite.
Opposite how?
Over time, the information in these systems, it doesn't get more chaotic. It compresses, it optimizes itself.
Wait, you're saying the virus mutations, they were actually simplifying its own code?
That's what his analysis showed, yeah. He looked at the SARS-CoV-2 genome as it evolved. The mutations that won out, the ones that survived, were the ones that actually reduced the total information content. The code got more efficient.
Why would it do that?
Yeah.
Survival of the fittest usually means stronger, not tidier.
And that is the million-dollar question. To Vopson, this looks suspiciously like a computer algorithm.
Like a zip file.
Exactly like a zip file. Why do you zip a file?
To save space, to save RAM.
Because there's a constraint. Vopson is arguing that this behavior suggests there's a constraint on the processing power of whatever is running the universe.
Wow, so the universe is running a compression script on itself because the server is getting full.
That's the analogy. If you're simulating trillions of particles, you compress where you can.
This all feels very philosophical, though. It looks like a computer. How do you actually test it? What's the smoking gun?
Yes, this is what pulls it out of the dorm room and into the lab. He's proposed an experiment using matter-antimatter annihilation.
Okay, walk us through this.
It's standard particle physics, but with a new prediction. You take a positron, the antimatter version of an electron, and you smash it into an electron.
And they annihilate, boom, pure energy.
Correct. The standard model says you get 2 gamma-ray photons, the particles vanish, mass converted to energy.
So where does the information part come in?
Remember Vopson's equation. Mass equals energy plus information. That particle wasn't just mass, it contained data. It's electronness.
So if you destroy the particle...
You have to destroy the information. And you can't just delete it, that energy has to go somewhere.
He thinks we're missing part of the explosion.
He predicts that in addition to the 2 gamma rays, we should detect 2 very low energy infrared photons at a very specific wavelength, around 50 micrometers.
And those photons are, what, the ghost of the electron?
Think of it as the heat from wiping a hard drive. It's the energy released by the act of erasing the particle's data.
Okay, that makes sense.
If we run this experiment and we find those specific infrared photons, it would be the first real evidence that our universe is fundamentally code.
That reality is just data, which is a little terrifying. But also, it's a perfect transition, actually. Because if the universe is code, we're getting way better at writing our own. We're shifting from the theoretical to a massive practical breakthrough.
You're talking about the fusion news.
The Princeton Fusion Prize.
Right, from asking, are we in a sim, to, well, building a star in a jar.
Fusion, the holy grail, the energy of the future. And it always will be.
That's the joke, isn't it? It's been 30 years away for the last 60 years.
But this source suggests we might finally be breaking that loop. And it comes down to a problem they describe as trying to hold wobbly jelly.
A very good description of plasma. So fusion is what powers the sun, right? You smash hydrogen atoms together so hard they fuse into helium.
And that releases a crazy amount of energy.
A massive amount. But to do it, you need temperatures hotter than the center of the sun. We're talking 100 million degrees Celsius.
So you can't just put it in a box.
No, you contain it with magnets. In a donut-shaped machine called a Tokamak. But the plasma, it's incredibly unstable. It wants to escape.
The wobbles.
Exactly. These instabilities can cause the plasma to touch the wall of the reactor.
Which is bad.
Very bad. The reaction dies, and you could damage a multi-billion-dollar machine, and it happens in milliseconds. Way too fast for a human to react.
So you're always just reacting to the chaos.
You're chasing it. Until now.
This is where the AI comes in. The source says they move from 2D to 3D. What does that mean?
So this Princeton team, they used deep reinforcement learning. They realized the old control systems, which treated the magnetic fields in 2D, just weren't enough. The plasma is a 3D object.
And how do you train an AI to control a sun? You can't just let it mess around with a real reactor.
You can't, so you train it in a simulation.
We're back to simulations.
We are. They fed it millions of data points from past experiments. The AI learned to recognize the tiny, subtle magnetic fingerprints that show up before an instability even starts.
So it's predictive. It's proactive.
It sees the future, milliseconds ahead. It sees a wobble about to form and adjusts the 3D magnetic fields to smother it before it's even born.
That's amazing. It's like it's automating stability.
It basically turns fusion from this unsolvable physics mystery into a control systems problem. And that's a problem we know how to solve.
So we're using an AI trained in a simulation to control a star, which might prove we're living in a simulation. My head hurts.
It's all just information processing at every scale.
Well, speaking of that, AI isn't just tackling the massive scale, it's also looking at the microscopic.
Yeah.
We have a study here from Washington State University. This one's about blocking viruses.
Right. Another case where AI is cutting through a level of complexity that's just, it's too much for the human brain alone.
They call it a lock and key mechanism.
Yeah. A virus, whether it's flu or HIV, it can't do anything on its own. It has to break into one of our cells to reproduce.
And to do that, it uses these things on its surface called fusion proteins.
Think of them as a very complex shape-shifting key. It has to bind to our cell and then physically change shape to pull the two membranes together until they fuse.
And then it's game over.
Game over. So for years, the goal has been to jam that key, stop it from changing shape.
But these proteins are huge and complex. So finding the right spot to jam is like a needle in a haystack.
A massive haystack. And you'd traditionally test thousands of compounds in a lab hoping one works. It takes years.
So the AI team, they simulated it.
Exactly. They built a digital model of the protein and had the AI analyze every single atomic interaction inside of it.
It's just number crunching on a massive scale.
And it worked. The AI crunched all that data and it found the critical weak points. For the Nipah virus, it pinpointed one single amino acid interaction.
One interaction.
Out of thousands.
One. It predicted that if you broke that one tiny bond, the whole key would jam. And did it work in the real world?
They took that data to the lab, made the change, and sure enough, the virus was locked out. Fusion efficiency dropped to almost 0.
That's incredible. It's taking years of guesswork and turning it into a single targeted experiment.
It's a roadmap. The AI tells the biologists exactly where to look. We're decoding the enemy.
Okay, before we wrap this up, I have one last quick-fire headline for you. This one's from the Weird But True file.
Let me guess. It involves fungi.
It does.
Yeah.
Researchers have proven that fungi can remember, and the headline says it could revolutionize computers.
Ah, yes, wetware. The idea that biology itself can be a computer.
How does a mushroom remember anything? It doesn't have a brain.
No central brain, but it has a network, the mycelium. It's like a biological internet. And they found if you give it a stimulus, like a pulse of light, it reacts. If you do it again, it reacts faster.
It learned. It stored the information.
It stored it in its physical structure. It's a form of biological memory. Now, I don't think we'll be buying mushroom MacBooks anytime soon.
I was about to ask.
But it opens the door to using biological systems for certain kinds of computation. The future might be a hybrid of silicon and, well, living tissue.
It all fits together.
It really does.
So let's try to synthesize all this. What's the big takeaway?
The big picture, I think, is that at every single scale, we're learning that nature is information. Whether it's the universe compressing its own data, or an AI stabilizing plasma, or another AI finding the weak point in a virus.
And we are finally building the tools to read and write that information.
Exactly. We're moving from being passive observers to active administrators. The stuff of science fiction is becoming the engineering problem of today.
And as we saw today, we're starting to solve them. It really gives you a lot to think about.
For sure.
Before we go, a quick request for you listening right now. If you enjoyed this deep dive, please check out the podcast title, The Podcast de Philippe.
We're trying to reach a milestone.
Yes, help us reach 2,000 subscribers. If you learned something new today, share the podcast with a friend. It really does help us out.
Thanks for listening.
Catch you on the next deep dive.